Hello everyone, my name is Yan Zhou. Today I want to talk about LeetCode problem 407, trapping rainwater 2. It's a hard problem and honestly the most fun one I worked on for this portfolio. So why this one? I'm sure most of you know trapping rainwater, the 1D version, is one of the most popular interview questions. Everyone knows how to solve it with a monotonic stack or two pointers. The problem is the 2D version of that, and jump from 2D to jump from 1D to 2D makes it way harder. You can't just use a stack or two pointers anymore. You need a completely different strategy. Okay, so we are given a 2D grid like this head map. Each cell has a number for how tall the bar is at the spot. The question, after it rains, how much water can this whole thing trap? In 1D, water only flows left or right, so a monotonic stack or two pointers work great. But in 2D version, water flows in four directions totally. So it's totally different ballgame. My first thought was brute force method. For each cell, do a BFS to find how much water it holds. Search outward to find the minimum height along all paths to the boundary. But I analyzed the complexity. Each BFS visited n times m cells, and in the maximum situation, they will visit n times m cells total. So the final time complexity is big O of n times m squared, with n and m up to 200. Yeah, 200. That's 1.6 billion operations. Way too slow. So I didn't bother coding it and moved on. And then I asked myself for a question. What decides how much water a cell holds? Obviously, the lowest wall around it. Water flows downhill. So instead of going inside out, go outside in, start from the boundary. Boundary cells never hold water. It flows off the edge. The shortest boundary cell is the weak spot, where water escapes first. Any neighbor can only fill up to its height. So we got the final algorithm. Put all boundary cells into a min heap and pop the smallest in every step. Check its neighbors. We'll get two cases. Case 1. Neighbor is shorter, like this. In this situation, we'll trap water and push neighbor to current height. In the case 2, neighbor is taller or equal. In this situation, no water, push with its own height. The final time complexity is big O of n times m times log n times m, because the priority queue or heap push or pop will span big O of log n. This is my CPP code. You can see in the first block, I get the n and m and define a priority queue. If you use Python, you can use heap queue. It's the same with the priority queue in CPP. Min heap stores height and coordinates of one cell. Greater makes smallest on top, because priority queue default is a max heap. So we need to use this operator to change it to min heap. And then this block will push our boundary cell, left and right columns, top and bottom rows. Like this boundary here. This is the key part of the program. In each step, we pop smallest cell and check 4 neighbors. For a shorter neighbor, add the difference to answer. Push with current height. Taller or equal, push with all height. Its own height. Each cell visited once, return the total. Its answer. Think of slowly pouring water around the terrain from outside. Water seeps in from the lowest boundary point, filling lowest spots first. The priority queue simulates this exactly, always processing the lowest cell guarantees correct water level at every interior cell. That's all. Thank you.